Hi everyone and welcome to the new video. In this video I will show you how to make a radiation detector from scratch using the ESP32 and the Geiger Muller tube. We will see how it works, we will implement several display modes. I will explain how the radiation detector works, how we can program it in MicroPython, and we will do several fun experiments. At the end of this video I will also show how to connect this detector to the cloud, and we will upload the data to the public GMCmap. I will also show how you can detect the radon level in your house with the radiation detector, vacuum cleaner and the sock. It will be fun. Without further ado, let's get into it. In this project I will be using MicroPython, but obviously this is a hardware project, so you will also need some hardware. And here is the breadboard I am using for the test. The main part of this board is ESP32 and I will program it in MicroPython. If you never used ESP32 before, I did a separate video about that. I will also use this small OLED screen to display the values. This screen is monochromatic, but it's good for our task and it's pretty bright. And last but not least, the most important part of this project is the Geiger Muller tube. You can easily buy a Geiger counter kit on Amazon if you search for radiation detector Arduino. This board itself is pretty old. It originally was made for Arduino, but it is also compatible with the ESP32. And it is really easy to use. You only need 3 wires, power, ground and the signal. So how does it technically works? The logic here is straightforward. This is a Geiger Muller tube. They are available in different sizes. As a general rule of thumb, the bigger the tube, the more sensitive it is. As you can see, I have several of them. One tube is already included with the board, so you don't need to buy it separately. And I will be using this SBM20 tube. It has a good sensitivity, but you can also use the tube included with the board. How does it technically works? This tube has a low pressure gas inside and the high voltage is applied to the tube. And when the charged particle is going through the tube, the gas becomes ionized and you get a pulse. This schematic converts the pulse to a safe 5 volts level. There is also a small speaker here, so you can hear the clicks. You can enable or disable it by putting this jumper. And technically that is easy. The output of the tube you connect to the ESP32 and we can start coding. The Geiger counter tube itself can be powered from the ESP32. It has on board high voltage converter that generates about 400 volts. The current is extremely low. You can even touch this tube and feel nothing, so this is safe. And as the last part of this project I will be using a small button that I will use to reset the values. But you can also use it for other purpose, for example to switch the screen modes or so on. And now when the hardware is clear, let's start with coding. Okay, at this moment we have an ESP32 and the Geiger Muller tube connected to the board. As a reminder, the Geiger Muller tube generates the pulse when it detects a charged particle. And our first task will be to count these particles. To do this I need to configure the pin as an input. MicroPython has internal support for that. I am importing the class pin. When I did a test, it turned out that the board can have a small noise, so I will ignore the values if they're coming too fast. I will use a bounce time of 2 milliseconds and I will show how it works. And to calculate the pulses, I will add 2 variables, a total number of pulses and the last trigger time. As a next step, I will create the function init.gpio. And as we can see, I will be using interrupt. I checked with the oscilloscope and it turned out that when there is a pulse, the level is going down. You can see on the screen how it works. When the pulse is detecting, we can see a lower value, so I'm using pin falling. To make the debugging easier, I will also use the internal LED, so we will see that it is blinking when the pulse is detected. And this is our interrupt handler. As we can see, the logic is simple. A last trigger time initially set to 0, and when the difference is more than 2 milliseconds, I increase the number of pulses. And I also set LED to 1, so we will see that this is on. Here is the tricky part that we need to know. When we initialize the board, we need to set the internal pull-up resistor to none. The Geiger counter board has its own pull-up, otherwise it does not work. And now we can implement the main loop. First I initialize the GPIO. We will add more complex logic here, but just for debugging I will reset LED back to 0 and let's see if we can get some pulses. And as we can see, it works. The result is really interesting even from a scientific perspective, despite the fact that the code is simple. And here we can make two important observations. First, what we can see is called the background radiation. As we can see, the radiation is never zero. While I'm talking, we can see that the LED is blinking. So there are always charging particles flying around us. This value is about 0.1 microsieverts per hour. We will see it later in more details when we will implement the screen. As a second test, I can take this object. This is a uranium glass made about 100 years ago in the 1930s or 1940s. And as we can see, when I put it near the Geiger-Müller tube, the blinking rate is drastically increasing. So the board works. As a second method, I will implement the reset button, and the logic here is simple. When the reset is triggered, I will reset all the values. And of course, I also need to add the button interrupt handler. So when the button is pressed, the code will be executed. Now we can detect the pulses from the Geiger-Müller tube, and let's go forward. Okay, as we can see at this moment, we can detect the pulses and calculate its amount. However, detecting every particle is not really practical, because all Geiger-Müller tubes are calibrated in the counts per minute and counts per second. This value is usually listed in the datasheet, and when we know the counts per minute, we can calculate the radiation dose in microsieverts per hour. So the most important parameter for us is the counts per minute and the counts per second. And the logic here will be simple. I will create an array that will store the counts per second, and from this value I will calculate counts per minute. Let's see how it works. I'm adding this variable. This is the maximum history length, and I will set it to 10 minutes, so it is 600 seconds. Then I will remember the time when we calculated the latest amount, and I will create the method calculate CPM that is doing the calculation. And as we can see, the first part is simple. If 1 second passes before the last method call, we have the number of pulses that appear during this second. When we have the number of pulses, we can add this to the list. Practically, this is our CPS, counts per second. The radiation decay itself is random, so it is important to have the history array to calculate the average values as well. And I will also increase the uptime value. The tricky part here is that when the board is started, we don't have enough data yet. And when the board is running more than a minute, I am using CPS history array. And when the calculation is done, I can save the last second value, so this loop will be executed again in the proper time. And now I can add this method to the main loop, but practically we will see nothing because the screen is not implemented yet. Let's connect the screen. As a reminder, I am using a small OLED screen. It has a resolution of about 128 pixels, which is enough for our task. This screen is using E2C protocol, and first I will add the implementation to our code. As we can see, I already created a screen needs update variable before, and now let's see how it works. In the main loop, I already calculated the CPM, and now I need to redraw the screen. The logic here will be simple. If the screen needs update, I will call the method update display, and I will reset this flag to false. And now we can use the screen. As a reminder, the CPM value was already calculated. It is a global variable. First I clean the screen, then I will call the method to calculate microsievert value. The logic here is simple. When we have counts per minute, we can calculate it to microsieverts per hour, but it depends on the tube. I am using the SBM20 Geiger-Müller tube, and the constant looks like this. If you are using different tube, the value is different. You can find it online. So with this method, I can calculate the radiation dose. Then I can print the counts per minute at the left, and I can print the radiation at the right. This library is using a fixed font with 8 pixels per character, so I can easily implement the right alignment. And as a final method, I will call OLED show, which will redraw the screen, and let's see how it works. I forgot to import the library. I need to add this to the top. Let's try again. And as we can see, it works. We can see the values. As we can see, the very first values are not very accurate. We need some time to calculate counts per minute because the radiation decay is random and it can be some natural fluctuation. And as we can see, the radiation level is correct. It is something about 0.1 microsieverts per hour, which is a normal rate. An obvious disadvantage of using counts per minute is a delay because it's an average. As a next step, let's add the graph so we can see the values in real time. And to do this, I will add the method draw CPS graph, which will draw the counts per second. As we can see, I'm using the graphic abilities of this library. I can use the method fillRect, and I'm just drawing the data on the screen. And the last thing I need to do is to add this. And as we can see, it is much more fun. We see the values on the screen. This screen is actually small, so I am displaying the values only for 1 minute, which is practically enough. And I can take the uranium glass jar and put it near the Geiger-Müller tube. And as we can see, the values are increasing very fast, so this Geiger-Müller tube is sensitive. However, the counts per minute value will be increasing slower because it's still an average. As an aside note, this uranium glass object is safe, the radiation is only on the surface. Even within 5-10 centimeters is practically equal to normal, so there is no danger here. And as we can see on the graph, the tube is pretty sensitive, we can immediately see the grow. With this graph I can easily see the values practically in real time, which is cool. And as we can see, the radiation detector works. Now it's already a good instrument, but let's improve the display and let's use different fonts. Okay, at this moment the radiation detector works and we can already use it. However, practically this screen is small and we can improve it. First, I want to use a larger font, and second, I can use special messages like low, medium or high, because not everyone knows what a microsievert is. To do this, I will implement a special large font mode. Here I need to make several improvements. ESP32 is not a normal OS and we cannot just use any font you want. First we need to convert the font to the Python script, and to convert the font to the ESP32 I will be using this library MicroPython font2py. It is easy to use, but it requires some steps. For example, let's say I want to use a large font to display the numbers. I will use a Roboto font for that, provided by Google. I enabled the terminal and I need to run this command. As we can see, I am using font2py script, which is available on GitHub. Then I specify the font I want to use, then I specify the font size, and font big is an output file that I will be using. And the last important parameters is characters I will use, because fonts can be large. For example, if I want to display the values, I need only character from 0 to 9. So here I run the command and it will create a Python file for us. As a next step, I will do the same conversion for the medium font. And as we can see, I'm using the font size 16. And I'm using the character set low, medium, large. This will be the values I want to show. And when it's done, I need to upload these values to the ESP32. For this I can use Tony IDE or I can use this mp command. But now it will fail because the IDE is open and the port is busy, but you can get the idea. And as the last step, I need to upload this writer class that I can take from GitHub. And we're ready to use the font. First I will import the files I created. As we can see, that is the writer class and font big and font medium. Then I will create an object that will draw the font. As we can see, I'm using two writer objects for big and for medium font. And now I will create a separate method update display large font. At the top of the screen I will display the CPM values as before. Then I will have the large values of microsieverts per hour. And I will be using large font for that. I want to center the image, so I am using this method string length, and then I can easily calculate the position. Then I want to show the units. In our case it's microsieverts per hour. If you want, you can use different units like rangens or something like this. And at the bottom of the screen I will use the text value, because not everyone knows what the microsieverts per hour is. I will create a separate method getDoseRate, and I will use a medium font for that. The getDoseRate method is easy. It will show only 3 text values, low, medium or high. So even if the person doesn't know about the radiation, it's immediately clear what's going on. And the last but not least, and if the font is large, I am using this new method, and let's run it and see how it works. And as we can see, it works and it looks cool now. First, the font is bigger and I can watch it from the big distance. Second, we can keep the board running and we will see the radiation dose. And as an example, I can put the uranium glass jar nearby and I can see that the dose is increasing. So our detector works. And as the last step, I will show how to upload the data to the cloud, and we can see our values on the public GMCmap. GMCmap is an interesting online service. It is supported by the GMC manufacturer. It also makes their own radiation detector, and if you have one, you can upload the data automatically, but you can also upload data with your own client, and I will show how to do it with an ESP32. The general idea is simple. You can see the map, you can see different places. For example, I live in the Netherlands, and if I scroll the map, I can see the data. The values here are displayed in CPM, in counts per minute. So as we can see, they can be different because different radiation detectors have different CPM values. In my opinion, it will be better to use microsieverts per hour, but this was their decision. I don't know why. And we can click every station and we can see the data, we can see the historical data and so on. For example, I click this station and I can see the data. GMC is also a well-known manufacturer. They have a lot of their own radiation detectors. You can see different models, and lots of models have Wi-Fi connectivity, so they can upload the data. You can go to account, you can select manage Geiger counters, and you can also edit device. And I already added a new device. I called it ESP32. When you create a device, you get a parameter like user ID, device ID. You can also fill additional information like the tube and so on. And now I will show how to write the code for it. Okay, our app is already working on the ESP32. And as the next step, let's upload the data to the GMCmap. First, as we know, ESP32 supports the Wi-Fi connectivity, so we need to make a Wi-Fi connection, otherwise we will not be able to upload. And as a first step, I will add the parameters. This is the fake values, obviously, you can put your real ones. As a next step, I will also create a network interface, and I will save the last upload time, because GMCmap allows us to upload every message in about 5 minutes. Now I will add the first helper method is Wi-Fi enabled. As we can see, the logic is simple. We must be sure that the settings are correct, because not everyone wants to upload the data. As a next step, I will add the method connect Wi-Fi. As the name suggests, the logic is simple. And when the Wi-Fi is connected, I can add the specific message on the screen. I will add connect Wi-Fi after init GPIO, and let's see if it works. And I can see that the Wi-Fi connected, we can go forward. The actual upload is pretty simple. We need to make a GET request. And as you can see here, the logic is simple. I created the method upload to GMCmap. As a first check, if the Wi-Fi is not connected but it is enabled, I am performing the connection. Then I have a global variable CPM value that was calculated before. I am also using CPM average and microsieverts per hour. And as we can see, the request itself is just a GET request with this form. And now, as we can guess, we need to add this logic to our main loop. Here I have a call to redraw the screen, and I will use the similar logic. If the time difference is bigger than our interval, then we upload the data, and then we save the new upload time, and technically that is it. Obviously there is a disadvantage here. As you can guess, the upload time can make 2-3 seconds or 1 second, and for this 1 second the screen will be frozen for a bit because the update display will not work. But we're uploading the data every 5 minutes, so freezing the screen for 1 second is not a problem. We should keep in mind that there is no multiprocessing or multithreading in MicroPython, so if we want to do a better solution, we can use async.io. And if you want me to make an async.io version of that, write in the comments below and maybe I will make a second part of the video. I forgot to add the method calculate average CPM. And as we can see, the logic here is simple. I am getting the data from the array. And now our code is done. Let's see how it works. As I mentioned before, GMCmap receives the data about once per 5 minutes. So we can see the data a bit later, but with the magic of the video you will see it right now. And several hours later, let's see the results. Here I open GMCmap. As I mentioned before, it is a public map available to everyone. I live in Amsterdam, and here we can see several stations which are uploading the data. And this is the data I uploaded. Here I can see the data on the map. Here I can see the value which is correct, 11 microsieverts per hour. Here I can see the CPM data, average CPM. As we can see, everything works. I can also open history data and see it. And now when our radiation detector is fully functional, let's make several scientific experiments with that. And our first experiment will be the easiest one. We just watch the screen and do nothing. And what we see here is called the background radiation, and it's actually interesting. Some people may be afraid of the radiation, but it is actually always around us. 80% of the radiation comes from the natural sources, like ground or cosmic rays and so on. Many objects are naturally radioactive. For example, you can put the radiation detector on every granite building and you can see the increase of the radiation level. But even without granite, you can see that the radiation level is never zero, and thousands or even millions of particles going through our bodies every minute. Another interesting thing here is the fact that the radiation decay is random. I mean, it is truly physically random, not like a pseudo-random generator on your computer. And actually, with a small update of this code, you can make a scientifically proved random generator. Radioactive decay is random, but it will be not so fast. As we can see, this Geiger-Müller tube detects 20-30 counts per minute, so you cannot generate too many numbers, but as a password generator it can be good enough. And our second experiment will be even more interesting. We can see real nuclear physics on our desk. What if I tell you that you can measure the radioactive decay of polonium or lead without any lab-grade equipment or special radioactive sources? And indeed, you can do it at home with two very scientific tools, a vacuum cleaner and a sock. So how does it technically works? First I need a sock. I put a sock on the vacuum cleaner and I will keep it running for several minutes. The more the better, you can run it for 10 or 20 minutes. In my case, 5 minutes were enough. And after that, I put the sock back on the radiation detector. And we can see that the radiation level is increasing. What on earth is going on here? And the answer is really interesting. The radiation increase is caused by the radon gas. There is practically always a small amount of radon that is emitted by the soil. And here on the screen we can see a radon decay chain. As we can see, it is a radioactive gas with a decay of about 3.8 days. Radon is a noble gas, has no taste or odor, and it's decayed to the polonium, and polonium decays to lead, and then we get bismuth. And the half-life of polonium is only 3 minutes, and the half-life of radioactive lead is about 26 minutes, and so on. And these ionized particles emitting by the radioactive decaying are slightly charged, so they are attracted by the dust. And what the vacuum cleaner here is doing, when the air is going through the sock, the radioactive dust stays on the sock, and we can measure it. To verify that there is no mistake here, I can measure the sock with a highly sensitive GMC radiation detector. And as we can see, it also shows that the radiation is higher than normal. You can keep the sock for several hours and you can save the data in CSV. This way you can measure the speed of the radioactive decay. I will keep it as a homework for the viewers. Write your results in the comments below. This is even scary to think about. This radioactive decay happens always, also in your lungs. And statistically, the radon is the second cause of the lungs cancer after smoking. And as an aside note, if your radon levels are too high, it makes sense to buy a radon detector. And then you can install a radon mitigation system, but this is a bit off topic for this video. And the third experiment I want to show is also fun. The Geiger-Müller tube is detecting the radiation, but actually there are different radiation types. Alpha radiation is a stream of heavy helium nuclei, beta radiation is a stream of high energy electrons, and gamma radiation is a stream of photons. This Geiger-Müller tube is sensitive to beta and gamma. Obviously we cannot see the electrons with the naked eye, but we can make a simple experiment. And here I have a small jar covered with the uranium glaze. This technology was popular in the 1930s. This jar is a strong beta emitter and it also emits some gamma. And this is our radiation detector, and we can see the background radiation, which is normal. Now I put the jar, and as we can see the level is much higher, which is also normal for this jar. And the interesting fact is that the beta radiation can be blocked by any dense object. For example, I can use this transport card for this. And now I am covering the tube with the transport card. And we can see that the level is significantly decreasing. Gamma radiation has much higher penetrating power and gamma rays are going through the card, but beta radiation is blocked and we can easily see it on the screen. Despite the fact that we cannot see the electrons with the naked eye, we can easily see how much beta and how much gamma this jar emits. If you also want to measure alpha radiation, you can buy a special Geiger-Müller tube with a thin window and connect it to the same board, and it will also work. It can be fun to do it. If you want to see the results, write in the comments below and maybe I will make a second part of this video. And that's it for this video. Thanks for watching. I hope that you learned something new. The full source code for this project is available on my Patreon page. Feel free to visit it if you want. This support helps me to buy things like this for testing. Press like and subscribe if you want to see more videos like that. Thanks for watching and see you next time.